So this is joint work with my advisor, Rafael, and our co-authors, Shir and Akash. So I'll start by talking about like the classical Sylvester-Gallai theorem. So in like the late 1800s, Sylvester posed the following problem, right? He asked whether you can draw finite sets of points such that the line through any 2 points contains a third point, right? So such lines are called special lines because, ordinarily you expect a line to pass through 2 points, but then, these special lines, they pass through like more than 2 points. And one obvious way to do this is you just pick a bunch of points on a line, right? And now if you pick any 2 points and join them, then, that line is special. So then the question is, can you do this like non-trivially, right? And you can try to do this. Maybe you just start by picking 3 points, and then you draw a bunch of lines to them. But all of these lines are now ordinary, so you need to put more points on these lines. But now every time you put a point, you end up with like more ordinary lines, right? You won't end up with a case where none of your lines are ordinary. And if you keep trying to do this, you'll sort of realize that you can't. And so in the 1940s, independently, Melker and Gallai proved that it's impossible to do so. So what they showed is that if you have a finite set of points such that any line joining 2 points is special, then actually all your points lie on one line, right? We can look at this as a local global theorem of sorts, in the sense we have this local condition, or we have many local conditions where the line joining any pair of points is special, and we have like this global consequence that the whole configuration has a small dimension. And when I say the configuration has small dimension, I mean that the linear space it spans has small dimension, right? In this case, it's just 1. So I just want to remark that this depends on the base field. The Sylvester-Gallai theorem, as proved by Melker and Gallai, works when your base field is the reals. Over the complex numbers, there are counterexamples. There is this Hesse configuration, which is 9 points. It's basically the inflection points on a plane cubic. And these lines are curved, but if you draw them, they're actually straight if you look at them in the complex plane. And all of these lines are special. So Serre asked if the Sylvester-Gallai theorem is true over the complex numbers. And using the results of Hirzebruch, Kelly proved that it's true. The points might span a plane, but it's still true that if all your lines are special, then the configuration spans some low-dimensional space, right? And okay, so there's like a number of ways you can generalize this theorem, and like roughly the main thing what you can do is you can weaken these local conditions and ask when you still have this sort of global consequence, right? So one natural way of doing this is suppose now you have like a configuration where for every point in your configuration, for some fraction of the other points, the line joining them is special, right? So what can you prove about these configurations? So for example, if you look at this picture, if you pick any point in this configuration, for about half the other points, the line joining them is special. But obviously, all these points don't lie on a line. And fairly recently, in a series of works, it was proved that under this weakened local condition, so where for every point, some constant fraction of the other points lie on a special line, all your points must lie in some low-dimensional vector space, right? So the dimension of your vector space is like 1 by delta, and this is sort of tight. And this is called like the robust Sylvester-Gallai theorem. And then the other question you can ask is, what about special planes, right? Or special affine spaces of like higher dimension. So let's say you consider every 3 points in your configuration, you look at like the 2-dimensional affine space they span, and then you say that this is special. So this contains more than the expected number of points. What can you say? And so Hansen proved that such configurations also lie in low-dimensional spaces when the underlying field is real. And it was also proved later that if the underlying field is complex, then this result still holds, right? Okay. So okay. So to talk more about this, so the way that I stated these theorems right now, they're like these statements about geometry. So to talk more about them and to be able to work with them, it's like sort of useful to translate them. On the plane, we have this line-point duality, right? Where points correspond to lines, and lines between points correspond to points on the intersection of lines. And under this duality, we can sort of rewrite the linear Sylvester-Gallai theorem like this. So we now, instead of a bunch of points, what we have is a collection of linear forms, right? And the condition that, so to capture the fact that the intersection of two lines has a third line passing through it, I can say that for every pair of linear forms in your set, so for every Li and Lj, there is some form Lk such that Lk is in the radical of Li and Lj, right? This just captures that geometric condition. So under this assumption, all your linear forms lie in some low-dimensional vector space, right? Also, yeah, so when you're working with linear forms, like the radical of an ideal generated by linear forms is just the ideal itself. So like the radical thing doesn't do anything, but it's indicative of what to come. Okay, so why are these things interesting to us? They have a lot of applications in theoretical computer science. So the robust versions were used to study locally correctable codes. In particular, you have bounds on locally correctable codes with a small number of queries using these configurations. And they were also used for circuit reconstruction. And the high-dimensional versions were used to give depth 3 PIT, right? And this last application is sort of what motivates the objects we study. So I'll just spend some time talking about this. So just a quick reminder, what's an algebraic circuit? An algebraic circuit is like a very natural model for computing polynomials. This is just like a definition by example. You have a graph. Every node either has a multiplication gate or an addition gate, or it's labeled by a variable, and every node computes the obvious polynomial, right? So this thing computes x plus y, this thing squares it, and so on. And this gate at the top computes this polynomial, right? The constants on the wires just scale what is computed. But now if you notice, this polynomial is just the zero polynomial, right? So what this shows us is that these algebraic circuits, it is possible for like non-trivial algebraic circuits to compute the zero polynomial. And it is a very important sort of problem in complexity to find out, given a circuit, whether or not it computes the zero polynomial. And you want to do this deterministically. It's fairly easy to do this using a randomized algorithm, because you can just evaluate the circuit at a random input. But the thing is, can you do this deterministically, right? And this is the polynomial identity testing problem. It's a pretty fundamental problem. It has applications in algorithms and in complexity theory. And it is pretty hard. In part, the hardness is explained by this seminal result of Kavanaugh and Impagliazzo, who showed that if you can deterministically de-randomize PIT, or sorry, if you can deterministically do PIT, then you have like, you will get very, very strong lower bounds. And these lower bounds are like much better than any lower bounds we know right now. Right? Okay, so since we can't do PIT in general, or like it's a super hard problem, we can try and do some cases. We can restrict our inputs and then try and solve some easier cases. So one thing you can do is you can put some syntactic restrictions on your circuit, right? And one way you do this is, okay, let's just say I'm only going to look at circuits of depth 3, right? And then I'm going to say that my circuit has 3 layers, an addition layer, a product layer, and another addition layer. And such circuits compute essentially sums of products of linear forms, right? So I give you a circuit like this. It computes a sum of products of linear forms. Can you do PIT? Or can you test whether or not it's 0? Okay, so here's like a pretty nice observation. If you have such a circuit that computes 0, let's just say there's 3 summons for now. If you pick an alpha such that L1 alpha and G1 alpha are 0, and then you evaluate everything at alpha, this last summon, the product of HI, is 0, right? And so algebraically, what this means is that for some index A, one of the linear forms, HA, lies in the radical of the ideal generated by F1 and G1. But in this case, it's just the same as the ideal generated by F1 and G1, right? And note that F1 and G1 are not special. This happens for every Fi and Gj. And also, the choice of picking L and G is also not special. I could have picked 2 linear forms from 2 different sets, right? And now this condition in red sort of looks like the linear Sylvester-Gallai condition that I spoke about earlier. And so in the 1960s, Edison and Kelly proved that if you have three sets of linear forms that satisfy this condition in red, then their span is small, right? And okay, so this works when you have three summons. When you have more than three summons, this exact idea, so this exact proof doesn't go through. We don't have like a Edison-Kelly type theorem for more than three summons. But Kayal and Saraf, and then later Saxena and Seshadri, showed that even if you have more than three summons, using roughly the same idea, the fact that you can pick one linear form from each of your gates, set them to 0, and then the last summon vanishes. Using essentially this idea, they showed that if you have a depth-free circuit that computes 0, then all the linear forms occurring in that circuit have a small dimension, right? And they proved this using the k-dimensional Sylvester-Gallai theorem. And combined with some results of Karnin and Shpilka, this gives us PIT for depth-free circuits where, yeah.
Sorry, what's F1 here?
Oh, sorry. That should be L1, my bad. It should say L1. Sorry about that. I hope that didn't cause some confusion. Okay. Okay. And then, so this gives us PIT for depth-free circuits with bounded top fanning. And then, so the next sort of class of circuits you can compute is, or you can consider is like depth-4 circuits, right? So now you have an additional product gate at the bottom. And such circuits, they compute sums of products of sparse polynomials. So instead of sums of products of linear forms, they compute sums of products of sparse polynomials. So we'll mostly think of them as, so we'll just focus on the case where the sparse polynomials are actually low degree, like maybe degree 2, degree 3, whatever. And okay, so like the polynomial they compute looks like this. And we can try doing the same thing. So you have P1 and Q1, and then you just pick a common root of P1 and Q1, and then you just evaluate the circuit at that point. And then the last summon again vanishes, right? So in this case, all you can say is that this last summon, the product of Ri, it lies in the radical of the ideal generated by P1 and Q1, right? It is a weaker thing than you. So in the linear case, you could drop the product, but here you can't drop the product, right? So you just have like the product of Ri lies in this radical. And so in 2014, Gupta conjectured that under these conditions, or these polynomials, the Pi, Qi, and Ri, they must span some low-dimensional vector space, right? He conjectured that what happens in the linear case should also happen here. And okay, so his conjectures were a bit stronger. They don't just work for 3 gates; they also work for like any k gates. But along with this conjecture, he used some existing results to show that we can get polynomial time PIT for depth 4 circuits if you prove whatever it is he conjectured, right? So the point is, he showed that it's sort of interesting to study these Sylvester-Gallai type configurations where you're working with higher degree polynomials and not just linear forms, right? So just, I would just want to say that there has been other progress on depth 4 PIT recently using, so this is Datta, Dwivedi, and Saxena using the Jacobian method. They gave quasi-polynomial time PIT for the same bounded top and depth 4 circuits. And the Limay, Shrikant, and Tavenis lower bounds for constant depth circuits, along with hardness randomness trade-offs for constant depth circuits, also imply sub-exponential time PIT for this model. But both of these are far from like what we actually want, which is like polynomial time PIT. The only polynomial time PIT we know for something that looks like this is for the very special case of depth 4 circuits where the top finite is 3 and the bottom product gates have in degree 2. And so this was a result by Peleg and Shpilka. And they basically proved this by proving Gupta's conjecture in the special case, right? So it seems right now the only approach we have for polynomial time PIT seems to be like using these Sylvester-Gallai theorems, right? Okay. So now that hopefully I've motivated why it's important, like why it's nice to study these, I'll just define these things. So what's a higher degree Silver-Segalai configuration? So now what you have is, instead of a collection of linear forms, you have a collection of forms of degree at most d. And you call this a d-radical Silver-Segalai configuration if for every pair of forms in your set, there is, so for every fi and fj, there is some fk that lies in the radical of the ideal generated by fi and fj, right? And so one of Gupta's many conjectures was that d-radical Silver-Segalai configurations span low-dimensional vector spaces, right? And so there is some previous work on exactly this conjecture. So a couple of years ago, Spilka showed that 2 radical Silver-Segalai configurations have small dimension. And much more recently, Oliveira and Sengupta showed that 3 radical Silver-Segalai configurations have small dimension. And there's also some line of other work showing some other variants, like the robust version for degree 2. So 2 radical, like the robust version of the 2 radical Silver-Segalai configurations have small dimension, and so on. So what's our result? So our result here is that it's like a high-dimensional version of like the quadratic Silver-Segalai theorem. So now we have a finite set of irreducible forms of degree at most 2, with the property that for every k plus 1 forms in your configuration, so f1 through fk plus 1, there is some form r which is different from fk plus 1 that non-trivially lies in the radical of the ideal generated by f1 through fk plus 1, right? So the set minus thing is some sort of non-degeneracy condition. We can just ignore that. So under this assumption, we showed that all your forms span some low-dimensional vector space, right? And so our main theorem implies the result, the linear high-dimensional Silver-Segalai theorem, like the result of Hansen, if you just assume all your forms are linear. And it also implies Spilker's 2 radical Silver-Segalai theorem if you just assume that k equals 1, right? Okay. Okay. So that is like the informal statement of the main theorem. And so before we sort of look at how the proof goes, it is instructive to look at how Spilker proved his result about 2 radical Silver-Segalai configurations, because we will, at a very high level, follow the same proof strategy, but looking at this will also highlight where the difficulty is when you want k to be bigger. So notice that if for many pairs of polynomials in your configuration, if the ideal they generate is radical, then what you have is just a robust linear configuration, right? Because if f1 and f2 is a radical, if f1 and f2 generate a radical ideal, then the condition that f3 lies in the radical of f1 and f2 is the same as saying f3 lies in the span of f1 and f2. So if most of the ideals generated by pairs of polynomials in your configuration are radical, then you're done because you just have like a linear configuration. So the interesting case is to look at when these ideals are not radical, right? So what Spilker did is he classified all the ideals of the form f1 and f2. In particular, he said that if these ideals are not radical, then either they span a square or they lie in an ideal generated by 2 linear forms, right? So this classification is based on the primary so essentially it's based on the primary decomposition of f1 and f2. You do the primary decomposition, you look at what primes occur, you look at what their degrees are and what multiplicity they have, and then you can deduce this. And this gives us some structure for many of the polynomials in your configuration. And he used the structure to reduce to the linear case, right? In some way. Okay. So the issue with that approach, when you try to prove higher dimensional versions, is ideals with k generators are much more complicated than ideals with just two generators, right? So in particular, they can have very large degree. Since you have k ideals, since you have an ideal generated by k quadratics, you expect its degree to be like 2 to the k. And if you want to study the minimal primes and the primary decomposition, there's like a lot more things can go wrong, because your ideal can have smaller codimension than what you expect. So this is the ideal of the twisted cubic. You expect it to have codimension 3, but it has codimension 2. And your ideal can also be mixed. Like you can end up with minimal primes of different codimensions. So because of these issues, and it seems sort of hopeless to do a classification the way Spilker did for ideals generated by two quadratics. So what we do is, so what we have to do is, we still have to show some sort of structure theorem, but our structure theorem is going to end up much weaker than the one that Spilker had, but it's going to be more general in the sense we can actually apply it to our case. Okay. So in the last couple of minutes, I'll just quickly go over roughly what the proof sketch is, or like at least the proof strategy. Okay. So we're working with like a bunch of quadratics, right? And Carlini defined this notion of essential variables, where so for any quadratic form, what is the smallest number of linear forms such that you can write your quadratic just purely in terms of these linear forms, right? So for example, if your quadratic is x squared plus yz, then x, y, and z are the essential variables. And if it's x squared plus 2xy plus y squared, then x plus y is the only essential variable. And the number of essential variables is, in some sense, a measure of the complexity of your quadratic, right? The more essential variables it has, the more complex it is. And so we now want to show that our quadratics lie in some low-dimensional vector space. So it suffices to find some small number of variables, like a constant number of variables, y1 to yr, such that all your polynomials are in the algebra generated by these variables, right? So what is the natural thing to do? It's like, okay, you start with y being the empty set. You look at those variables that occur in many polynomials, and you then just add them to y, right? It's like you're just trying to do some you're just trying to apply some combinatorics to the problem. Like I just drew a picture because it's easier to explain. Think of the black circle as all the variables. Each of the red circles represents the essential variables of one of the polynomials in your configuration. And in the middle, we have this place where many of the circles intersect. So we just add all of these to our set y. The blue circle represents the set y we're constructing. And then similarly, a little to the left, you also have a place where many things intersect. So you just add that to y, and so on. And so after you do this, what you're left with, for every form, fi, the things that you're left with are the sort of extra essential variables, right? It's like the smallest s such that you need s more variables in order to put fi in the algebra you're constructing. And at least intuitively, you want to iteratively increase the size of y. And the place where you can't do this anymore is if you have many forms with disjoint extra variables, right? Because at this point, you can't increase y by a small amount while reducing the complexity of many polynomials in your configuration. So we capture this, or we give these sets of polynomials a name. So if you just collect t polynomials that don't lie in the ideal generated by y, and such that the extra variables are disjoint, then we call such sequences like integral sequences. For example, if your set y is just a singleton, which is one variable y, f1 could be like x squared plus yw, f2 could be uv plus y squared, f3 could be ab plus cd. So I've highlighted all the extra variables. And these are like obviously disjoint. And our structure theorem is that integral sequences of irreducible forms generate radical ideals, right? Okay, so if we sort of go back to like the proof idea, the bad case is when we had many polynomials with disjoint variables. But by the structure theorem, what this tells us is that many of the ideals generated by tuples of forms in our configuration are radical, right? Because their extra variables are disjoint. But if many such ideals are radical, then actually what we have is just a linear configuration, maybe like a robust high-dimensional linear configuration, right? And we know how to control these. Like there's theorems that say that such configurations have like bounded span. So in the bad case, we can use the linear configurations to control all the remaining forms, right? So that is like roughly that's roughly our proof strategy. Okay, so just a quick remark. So the way I stated the structure theorem, it doesn't really look like the structure theorem of Spilka. But if you just write the contrapositive, then what our theorem says is if you have a sequence of forms and they generate an ideal that's not radical, then one of the variables of ft has to occur in f1 through ft minus 1. Right? And now it starts to look more like this theorem of Spilka. Although the previous structure theorems give us more information, but we don't need that information to do the combinatorial arguments. Okay, so that is sort of how we did our proof. I'll just quickly finish. So in conclusion, we proved a higher dimensional analog of quadratic Sylvester-Gallai configurations, generalizing the results of Spilka and Hansen. And the sort of main contribution is some new techniques to handle higher codimensional ideals, which we hope will generalize more easily when we want to prove more theorems of this nature. And there's two open problems. Both of these are actually the same open problem, which is can we do depth for PIT in polynomial time? But there's two sort of ways we can do this in the Sylvester-Gallai framework. One is you prove stronger Sylvester-Gallai theorems and try and get exactly the theorem that Gupta conjectured. For that, you need to prove many variants of these theorems, like variants where each of your forms is colored and some product versions, or there's a bunch of variants. The other thing you can do is you can strengthen the connection between PIT and the Sylvester-Gallai theorem and weaken what theorems you need to get PIT in some sense. Okay, so for example, Saxena and Seshadri showed that they showed a direct connection between the rank of depth 3 circuits and the bound on k-dimensional linear Sylvester-Gallai theorems. So if you can do something direct like this for let's say quadratics or something, then we'll already have depth for PIT with the bottom in degrees too. So both these open problems are I could have just equivalently said, can we do depth for PIT in polynomial time? Yeah. Oh, yeah, that's the end. Yeah.
So I may have missed this in your presentation, but what does your theorem imply about PIT?
Oh, so what we prove right now still does not. It's just so the exact conjectures that we need for PIT are sort of stronger than what we prove right now. It's just one step in that direction. Yeah. So maybe offline I can tell you what the exact conjecture is and but yeah.